For differential equations, lesson 5.1, day 3, now we will have damped motion. So we're going to talk about this over more than one day, but let's have our day 1 on this. Free damp motion, day 1. Free harmonic motion is somewhat unrealistic because the assumption is there are no retarding forces acting on the moving mass. Obviously, if we were to drop a spring or drop a mass from a spring, we wouldn't see it forever oscillating. That's unless there is a perfect vacuum. There will at least be a resisting force due to the surrounding medium. And these damping forces are considered to be proportional to a power of the instantaneous velocity. So this is equivalent to having a constant multiple of dx dt. So when we had undamped motion, what we started off with was an equation, and of course we simplify that. That second derivative was just equal to opposite of kx, but now we're going to say, look, we very well are going to have another issue arising, and that would be a proportional situation with the instantaneous velocity. There's some constant, we could call it beta, multiplied to dx dt, and we're going to be subtracting that. So if we're working with this, we can definitely then move over this way. So remember, this would be going in with resistance to it. That's why we're putting that minus in front of it, much like a restraining force, slowing it down, so to speak. So we could have our md squared x dt squared. If we bring that beta dx dt all over to the left side plus kx, we still have a second order differential equation. We could very quickly divide by m. That would very quickly lead us to a nice second order differential equation, one that we would have constants with. But you might remember when we had k over m in blue here, we wanted to really redefine that as omega squared. With beta over m in yellow, we're going to see that we'd like to redefine that as 2 lambda. The reason why we're not just having a 1 lambda hopefully will become apparent in just a little bit, much the same way as we could solve as we did on our first section. Having omega squared was very helpful. Having a 2 lambda will be helpful as well. Well, hopefully what you're seeing is really our characteristic equation would arrive with an ax squared plus bx plus c kind of a pattern, if a quadratic. And the quadratic that you can see is you'd always have opposite b plus or minus the square root of b squared minus 4ac all over 2 times a. Of course, our characteristic equation would be m squared plus 2 lambda m plus omega squared. We could apply this quadratic formula here, where our a would be 1, our b would be 2 lambda, and our c would be omega squared. So let's use those substitutions right in here and see what our solutions will look like. Opposite b will have the opposite of 2 lambda, plus or minus. Well, b squared will be 4 lambda squared, minus a 4 times a 1 times omega squared. And then down below here we'll have 2 times 1, which is just a 2. I'll tell you what, if we were to continue to simplify here, we could very quickly realize that we could factor out a 4 from both of these. And the square root of 4, of course, is a 2, so then we'd have negative 2 lambda plus or minus a 2 square root of lambda squared minus omega squared all over a 2. And if we were to just divide out that 2 from all 3 parts, we'd be left with negative lambda plus or minus the square root of lambda squared minus omega squared all over 1, which, by the way, we could just plain and simply now come down and see our 2 characteristic solutions. We'll have negative lambda plus the square root of lambda squared minus omega squared, negative lambda minus the square root of lambda squared minus omega squared. And, of course, as we're looking here, that would mean that as we are looking at just even the first solution here, we'd have C1 times e to this negative lambda plus the square root of lambda squared minus omega squared. Look at that solution. Wow, that would be your t. And then, of course, we would have the subtracted form with C2. So, this is really what that form would look like. You'd see that the t would get distributed in for both. And that means that we could actually begin to just rewrite this ever so slightly. E to the negative lambda t times e to the t square root of lambda squared minus omega squared. And the reason why we can separate that is you can see the importance of seeing what is happening with that lambda squared minus omega squared. As we're really paying attention here, you can see that's obviously going to be what is inside that square root. And what we're going to see then is each of the solutions will have that damping factor of e to the negative lambda t. So lambda is going to be greater than 0. So we're going to definitely see that this displacement of the mass, it's going to become negligible as t increases. So what we're going to see is, and that would make sense of what we'd be seeing in the real world, of course, as t increases, we would want to see that the displacement of the mass becomes less and less of an issue. But really, let's talk about the sign of lambda squared minus omega squared. That is so critical and so important. You might not be too surprised to realize we've got trichotomy, 3 possibilities. Either lambda squared minus omega squared is positive, 0, or possibly negative. Let's deal with the first case. This lambda squared minus omega squared is positive. Remember where lambda is coming from. I'm going to just recopy for a moment that 2 lambda was beta all over the mass. And remember where omega squared is coming from. Omega squared is k over m. If you're going to have lambda being larger than omega, and that's what's going to happen is you're squaring lambda to be larger than 0. You want lambda to be greater. That means that really at the end of the day, omega of this beta right here, this beta has to be large compared to this k. So we would want beta to be larger than the k. What is that really saying? That we're going to have more of an impact of that resistance from the medium. We talked before that the surrounding medium is really going to be proportional to that instantaneous velocity. So if that's larger, if that beta factor is larger, we would expect to be over damped. It's going to not be able to oscillate and forever bounce around. Normally you would picture a spring to look something more like a sine or a cosine wave. It would appear to look something like so. But if you're over damped, that damping coefficient is large. So what would that look like as we would graph it? Well, you could see perhaps, here's one possibility. You could see perhaps that your curve is beginning to move, but it's getting dampened quite a bit. It's not going to be able to oscillate and continue to bounce around. It's getting really resisted to the point where it's going to slow down in a hurry. Perhaps you can move from a positive direction then to a negative, but that damping is going to stop the possibility of oscillatory motion of bouncing back and forth. So this is overdamped. This is where really that bouncing back and forth motion is killed. So that's case one. Case two, you can think, well, what if lambda squared minus omega squared was equal to 0? Well, if that was equal to 0, that means that these two parts right here, you'd have e to the 0, that's just going to be a 1. And you would expect, that to just be collapsing. So in other words, you'd have some constant of, e to the negative pi t. But remember what happens when we've got that discriminant equal to 0. That means you have double roots. And when you've got double roots, you want to make that adjustment of putting in a factor of t. This is what we call critically damped. Critically damped means any slight decrease in the damping force would result in oscillatory motion. So we're so close to being able to bounce back and forth. What could that look like? Well, you could see, something that would look more so like these two pictures. Critically damped, you're definitely damped, but just the slightest change is going to result in bouncing back and forth. Underdamped, what if lambda squared minus omega squared is less than 0? The system's said to be underdamped since the damping coefficient is small compared to the spring constant. Remember, the spring constant was tied to omega. The damping coefficient is found over by lambda. So if you're getting something negative, obviously omega squared is going to be larger than lambda squared. And the roots would be complex. The roots would be complex as we would have to pull out an I. You can see that we can switch the order here. But as we would have an imaginary component and then our real component, you can see that the way these graphs would work out, well, first the equation. We'd have e to this real component and then c1 cosine of that imaginary part, t plus c2 sine of that. Like we talked about yesterday, we could condense these two. It looks like they have the same arguments. So we would expect for them to have the same periods. They do. Just as we did yesterday, we could use that combination of a is equal to the square root of c1 squared plus c2 squared and condense this with a phase shift to just get one nice graph. What would this graph look like? What does it mean to be underdamped? Well, you will get some oscillatory motion. You're going to be bouncing back and forth, but there's a dampening. You can see that that distance moving up from your sinusoidal axis is going to lessen each time, and it's eventually going to get damped out where it just flat lines. So that was just our little introduction to these three different cases. We're going to have a second video in a moment showing you an actual problem.